Hello everyone, I thought I'd take a short break from my normal series of videos to share with you some really cool innovations that involve AI, Cisco's CML, and how MCP servers can be used to deliver cutting-edge automation right on your own lab setup. But before I tell you what an MCP server is, let me explain further the capabilities that this whole setup provides. Imagine that you have a specific topology in your mind and you want to describe it in natural language. Something like, I want 3 routers connected to each other with a loopback on each router. I want a single area OSPF configuration where all loopbacks are advertised. Now imagine CML takes that natural language prompt and interprets it and creates a topology with all of that already set up. Now that's really amazing, isn't it? I'll explain more about how this works and how you can deploy this for your own use. But first, let's talk about the key component to this whole setup, and that's the MCP server. Now, what is an MCP server? Well, MCP stands for Model Context Protocol. It's a relatively new concept that has come as part of the advent of AI large language models, or LLMs. MCP is a standardized protocol that lets AI models like ChatGPT or Claude and a whole series of others to securely and consistently access external tools, data sources, and services. In the context of Cisco's CML, MCP essentially sits on a server between the CML system and an AI LLM. In this sense, you can consider it as kind of a middleware, which appropriately takes the natural language explanation given to the LLM and transforms it into commands that instruct CML to create a lab topology. In other words, MCP is the single standard way for LLM models to plug into many different systems, including CML. You see, in AI, LLMs are isolated by default. In the context of a CML implementation, they don't know about CML systems, or your YAML files, or your topologies, or APIs, or your configurations. They only have direct access to their accumulated knowledge and not to external systems. So there's no way for the LLM to interact directly with your CML system and its resources. In the past, in order to achieve such interaction, you needed to set up a customized interface for each particular interaction. So you would need to set up your own customized API on CML and on the LLM to allow interaction. Now, this can be time-consuming, costly, prone to errors, and not easily repeatable for other systems. MCP simplifies this by creating an abstraction between the AI LLM and the system you want to interact with, which is CML in our case. So in short, an MCP server is a service that exposes tools, resources, and data using the MCP standard so that AI models can interact with external systems, such as Cisco's CML. So the AI LLM model never directly accesses your CML system, but it goes through the MCP server. Now, practically speaking, what does this mean? Let's say you want to create this topology here. Here we have an OSPF topology with a single backbone area, 3 non-backbone areas, a single ABR between areas 0 and 1, and between 0 and 2, and 2 ABRs between areas 0 and 3. And you have these networks here that you want to advertise using OSPF. Now you can go into CML and create this yourself. Depending on how fast you are, it may take you 5 to 10 minutes, maybe 20 minutes. Alternatively, you can describe this lab topology in words, just as I have done now, and you can have AI create this in your CML lab within seconds. And get this, you can either write it out or even give voice commands, just like any other AI interface, or even upload images with your topology to support and add additional context and info. Now, what's the benefit to all of this? Isn't CML there for us to learn how to lab up topologies? If I ask the LLM to do it for me, what's the point? Well, as you get more and more into labbing, you'll find that you often spend a lot of time on the initial lab setup. You'll notice for our previous lab topology example, we have 7 routers, 7 physical links with 14 interfaces, all requiring IP addresses plus 3 loopbacks. And that's just the topology itself before you even get to any OSPF configurations. Or think about this. If you want to lab up MPLS Layer 3 VPNs, you will need to first set up the customer, PE and P routers, the links, the interfaces, the IP addresses, and the OSPF or ISIS underlay. In some topologies, this may require a dozen routers with dozens of links. And all of this is before you even get into any MPLS or MPBGP or VRF configurations. The point is that whipping up an MPLS underlay network in a matter of seconds can be extremely helpful, ensuring you spend your most important study time setting up MPLS rather than simply configuring a whole bunch of interfaces with IP addresses, something that can be tedious, time-consuming, prone to errors, and of little learning value. So how do you set up an MCP server for your CML topology? Well, actually, it's not too hard. At this point, Cisco hasn't implemented this as an official part of the CML platform, but there's a lot of info and documentation out there to help you get up and running quickly. Here, I'll highlight the high-level steps you should take and the several choices you have to make in how you're going to employ the setup on your own devices. Now, there are 3 primary components that you will need: CML, an AI LLM, and the MCP server. Let's talk about each one of these separately. First of all, you'll need a running CML setup that's reachable from your local device. That is, your laptop or your desktop computer. It may be running remotely on the cloud, on another device you own, or on your own local computer. In any case, it should be reachable from your device in order to create the connection. I won't go into how to set up your CML. I assume you have that up and running already. I will, however, mention that you will have to ensure that you can automate your CML. Check out the API documentation page of CML. You can find that by going to Tools, API Docs. There you will see what an external tool, like an MCP server, is allowed to do with your CML server when authenticated to do so. Ensure that you have things like authentication, users, labs, systems, nodes, interfaces in that list, which simply identifies the things that can be manipulated by authenticated external tools like your MCP server. Now, once you confirm that your CML is up and running and it's modifiable via automation, we can then go on to our MCP server. Now, the MCP server can be deployed in several ways. The most common and simplest setup is typically deploying the MCP server locally on a Windows machine using Docker. This is the most popular setup because it's very fast to set up and you can safely deploy it on a device like a laptop rather than on a dedicated server because it's a non-production environment. It's just a lab setup and there are no high availability requirements. Docker makes this easy because it packages the MCP server and all its dependencies into a single repeatable unit without the need of configuring extra parameters in Python. You can install Docker Desktop on your Windows device, which essentially gives you a lightweight Linux environment using Windows Subsystem for Linux, or WSL, which is what actually runs the MCP server container. Now, once Docker Desktop is installed, the only thing you need to verify is that it's running and you can see the Docker icon in your system tray. Then you can prepare the MCP server configuration. This config tells your MCP server where to find the CML service, how to authenticate to the CML API, and which tools you want to expose and manipulate using MCP. Now, this typically requires Python, the use of the MCP server library, and the deployment of an additional Docker image. But luckily, there's a ready-made helper program called CML MCP that takes care of all of this in one package. This can be directly downloaded and installed using Docker and can be configured with appropriate dependencies, credentials, transport layer communication ports, and many other parameters for your CML instance. Now, once Docker and the configuration are ready, starting the MCP server is straightforward. Docker pulls the MCP server image, starts the container, and exposes a local port where the MCP protocol listens. From this point on, the MCP server is live and waiting for an AI client to connect. Now note that the steps and the commands to implement this vary greatly depending on the details of your deployment, but well-documented sources online can be found quite easily. Now the last step involves the AI LLM. Now at this point, you can use any LLM you like, but at the time of recording, Claude Desktop is the preferred LLM simply due to the fact that it was designed from the start to connect to local MCP servers. But it is possible with a bit of extra work to get it to function with other LLMs as well. How to do that and the implementation details for those are also well documented online. Now, to use Claude with MCP and CML, the setup is intentionally simple. You install Claude Desktop on your machine, and you configure it to connect to a local MCP server that we set up before. Because the MCP server is running on the same laptop or desktop, and it's already wired to the CML API, when Claude starts, it automatically discovers the tools exposed by the MCP server. From Claude's point of view, these tools just appear as safe, structured actions it can call. At that point, Claude isn't talking to CML directly, it's talking to the MCP, and the MCP is handling all interaction with CML. This keeps the setup local, fast, and secure, which is exactly what you want for a lab environment. Now at this point, you should be able to talk to your CML in natural language via the Claude Desktop interface. Now, the results of this setup are phenomenal. You can simply describe your lab into existence. You can do it incrementally or in one go. For example, you can say, deploy 3 routers and name them R1 to R3. Connect the routers together using gigabit Ethernet connections. Enable OSPF on all routers, and so on, so that you can make sure that each step is done correctly and you can check it along the way. Kind of like a normal discussion on an AI interface. Or you can describe it all together and have the system created all in one go. Now, while describing your topology, if there are any details of your configuration that you haven't stated, such as IP addresses for specific links, the LLM is intelligent enough to decide to put those in for you, suggesting specific address ranges. And if you choose to use your LLM's voice capabilities, you can speak your lab into existence. And this can be useful because it can be deployed even faster at the speed of thought, so to speak. Now, I know I haven't gone into more detail concerning deployment scenarios, and I've done this purposefully. I have found that when I set this up on my computer, there are so many different combinations of setups that there's no value in showing you my setup because it's bound to be different than yours and will require slightly different tweaks along the way. But the knowledge that you've gained will hopefully give you a head start in your deployment. Essentially, I'm sharing with you what I would have liked to have known when I decided to start learning about MCP and its use with CLM and AI LLMs. If you do end up using an MCP server for your CML topologies and your learning journey, you can save countless hours of preparation and setup in the long run, allowing you to focus more on the configurations that matter rather than the mundane and tedious initial setups that involve device deployment, startup configs, and link connections. Now, on my website at telecomTech.io, I will soon be planning to put in some courses that go more in depth into AI, CML, and MCP servers, so stay tuned for that. Well, that's it for this video. Don't forget to check out my other videos on networking and telecom technologies, and also check out everything I have available on my telecomTech.io website. I hope this has been helpful for you, and I'd like to thank you for watching.